Okay, so I thought I'd do a video on titration curves. Now most of you probably have mastered this, but it's a key concept for the course, so I wanted to make sure that everybody was on the same page. And the problem I think I'm going to use is the one that was on the first midterm and was also in the lab from week 4. And that's the titration of histidine. This should also be helpful to you if you're looking for help on the wet lab number 1, which involves titration of an amino acid, one of which could be histidine. So one of the reasons that this is a key concept for the course is that it's a graphical representation of the kinds of math that we've been doing on acid, base, and buffering capacities. So it shows you in a graphical way what the buffering capacity looks like. Another reason is that because biochemistry is very much an experimental science, and this is the kind of data that we might get in the analytical or biochemical laboratory that we could then plot and determine values from. So it's an important concept. And the whole thing centers around measurement and how we do it, and all of that is based on what an equivalent is. And this is a concept that a lot of people stumble over when they try to do titration curves. So in the example that was given on the test, we had 0.75 grams of our amino acid. That's better. 0.75 grams, and we're told that the molecular weight is 155.15 grams per mole. Okay, and we've put this in a beaker and we've made it up to 75 mils with water. So the first thing we have to figure out is how many moles of the weak acid do we have in the beaker? And that's going to define an equivalent. So we have 0.75 grams. Obviously, to make the units work, we've got to divide 0.75 grams by 155.15 grams per mole. And that is going to give us an answer in moles, which it turns out to be 0.004834 moles. Okay? That is an equivalent in this particular experiment that we're doing. Okay? Every experiment's going to be different, but it depends on how many moles you have in the beaker. Okay, so that is our definition of a mole. And then we have, in this particular example, we're given a number of volumes of 0.65 molar NaOH. So we're starting fully protonated as determined in the question, and we're going to add base, and we're going to titrate up the amino acids through its 3 pKa, starting from the lowest and going towards the highest. So we have to figure out for each of these, we're not going to plot mils versus pH, we're going to plot equivalents. So we have to have a way of getting from volume to equivalence. There's many ways you can do this with the math. I'm going to show you 2 ways. One way is kind of doing it in 2 steps, is to figure out how many moles of NaOH each addition is. So let's do it for the first one. It's 0.08 times 0.0001, if you like. That's not a good way of doing it. How about we say it's, we're going to convert 0.08 to liters and say that this is 0.00008 liters. Okay, I moved the decimal place 3 units that way to go from mils to liters, times my 0.65 moles per liter, which comes from here, the concentration of the base. This is going to give me a number of moles. In this case, this works out to 0.00052 moles of NaOH. Okay? Now we have to figure out how many equivalents that is. We will divide by this number here, which is number of moles in an equivalent. Okay? And we will end up figuring out how many equivalents we've added, which ends up being 0.0108 equivalents. That's the long way, but it's clearly defined. Figure out how many moles you've added, divide that by the number of moles there are in one equivalent. Another way to do it, and another way to do it quickly, is to say, all right, for each milliliter added, how many equivalents did I add? To do that, you figure out how many moles of NaOH there are in 1 milliliter. So 0.001 liters times 0.65 moles per liter gives me 0.00065 moles per ml. Okay? Now, if I divide that by the number of moles in an equivalent, I've written all over my graph anyway, I'm going to get an answer in equivalents per liter, or per milliliter, and that's 0.1345 equivalents per ml. And that turns out to be a really handy way of doing these. So I can say now very quickly 0.08 milliliters times 0.1345 equivalents per milliliter is going to give me the 0.0108 equivalents. And I can go through the table rather quickly. From there, you have to figure out what the pH is at each of these values. Okay, so I'm going to leave this math here. I'm going to get rid of some of this so we can figure out how to fill that out. Using the math that I just showed you, I would end up with 0.0108. This one turned out to be a little bit of a stinker on the test, but that was okay. 0.09415, 0.2152, and 0.4708. Okay? So there's two things here. The first one is you got to figure out which pKa to use. We're starting off fully protonated, means that everything has its protons still attached, and we're adding base and going up. So we're going to start from the lowest pKa and work towards the highest. So in this case, that was 1.82. Call it pKa 1 equals 1.82. Now, we started off, everything was in the HA form. I'm going to use the second point because the first one gave us a negative number, which is hard to understand. So essentially, it's so close to 0 as to be indistinguishable from it. 0.0945 equivalents of OH added. What this means is, before I had essentially one full equivalent that was in HA. Now I've added this 0.09415 equivalents of OH, and that has deprotonated that number of equivalents into A minus. So what I have now is 0.09415 A minus and a little bit less of HA, whatever 1 minus that is. Okay? And this allows me to put this into the Henderson-Hasselbalch equation and solve for pH. So pH would be equal to pKa plus the log of A minus over HA. We solved that for all of our points. Now the first one gave a negative number, essentially 0. This gave 0.837, and we worked up from there. Now the only other tricky spot is when you get to filling your first equivalent, that group has now been fully deprotonated and we start to work on the next one. This is assuming the simplistic situation where there's no overlap between the two. And Duffy will show you that's not 100% true when you take analytical next year, but for now we're going to assume that they're separate entities. So once you get to the second pKa, you're going to ignore the first pKa. Or, for instance, if you look at the table, when you've added 11 mils, that turns out to be 1.4, I'm not really sure what that says, could say 4791. Equivalents, the one equivalent dealt with the first pKa, and so the only part we're going to look at is the 0.4791, that will be relating to the second pKa. And we'll use that number to calculate pHs with that second pKa. When all is said and done, you're going to plot this in pH, and you would never be so bad as to have your numbers all over the place like I am here, but anyway. Okay? And you're going to have equivalents along the bottom. Now you have 3 ionizable groups, therefore you need 3 equivalents. And it's equivalents, spelled correctly, of OH added. Okay? Please indicate what you're adding. Now the half equivalent is going to be really simple. I always go and put those in first. That's the easiest point to put on a titration curve. So our first pKa was 1.82, and we would run into that at the first half equivalent. At 1.5 equivalents, we'd run into the second one, which was 6.0. So there. And the third one was 9.18, which we would run into at 2.85. That's somewhere in here. Okay? So these 3 points, our pKa's, are important points. But you can see the shape around there is not just going to be a nice straight line. There's going to be flat parts and steep parts. And so the point of doing all these calculations is to fill in those points. It's going to look something like this when you fill them in. You're going to have flat bits around the pKa and steep bits between them. The flat bit is where you've got your maximum buffering capacity, and the steep bits is where you're not having maximum buffering capacity. And so hopefully with this kind of a method, you can go from titration curve to values and from values to titration curve, regardless of whether you're given volumes or given pHs or given equivalents. You could work one way or the other by understanding the basic premise of the equivalent and then how to get from that to plotting equivalence versus pH. So that's the long and the short of a titration curve, and hopefully you get the concept now.